Welcome to a new test and teardown video. Yeah, a good old Bang & Olufsen low distortion oscillator TG8. This one is a very special oscillator. It is specially optimized for low distortion. It's like 106 dB down. All its THD, it's like super clean sine waves. So this is absolutely top of the pops when it comes to good clean sine wave generator. So I really hope it works. There is a full manual and schematics and everything as usual on peel.dk. I will put a link to that if you want to know much more about this fantastic unit. Got a few little funny features here like common offload, and that is between the sync output and the sine wave or square wave output. You can even hit off and then there is no output. The output voltage, that's all those ranges. And there's of course the output voltage, so we should be able to see here how much we got. And all that is frequency. It goes from 1 Hertz to 100 kilohertz. Yeah, enough sneaky snacky. Let's try and see if this thing works. So let's see if this blows up. I think it's always a lot of fun to video the first power on. And we got output, and I really like the frequency indication here. So I'm in 1 kilohertz, so that means it's probably from 1 kilohertz and then to 10, right? Okay, so that so far that works. It's not a lot of, I mean, that's quite nice. And we're in sine wave, and look at that. Oy. That is a clean looking sine wave. Obviously I will try and see if I can analyze this, but I don't think I will be able to analyze better than 100 dB signals on that unit here. So let me try and work this out. Let's try and see if we can see anything. Oh, that is funny. When I started the phone to record, I actually saw some of these harmonics went up. I'll try and stop it again and see if that is really the case. Now let's try and see again if they go up. Or I think it's just me moving around here, touching the cable. That's probably what it is. Of course, this is very weak signals, and I'm recording a very long chunk of data every second here, and it's analyzed and all that kind of stuff. And this is 1 kilohertz sine wave, and that is of course all the harmonics. They're just there at every 1 kilohertz, but they're really quite low, aren't they? This is 20 dB per division, but I think it's actually the input stage of my scope here that is creating all those harmonics, because this can't be, you know, the real method of measuring this. You need to attenuate the fundamental and then look at the rest with a filter, and this is also explained very loud and clear in the manual of this instrument, how you do this, because otherwise you can't measure this. Of course I can change the scale here, and I can zoom out, and I can do all sorts of nice things, but this is not bad at all. Now it looks a lot more nice and smooth, adding a little bit of average. You can see using this measuring method, it's like minus 60 dB, the harmonics. I've adjusted the input level here to also be on the screen. So, well, let's play a little bit more with this unit. Let's just try and put it a little bit to the test here. Let's hammer it all the way to maximum frequency, maximum output, and then hammer this all the way up. So that is 10 volt RMS. And yeah, that is very close to 10 volt RMS, 28 volt peak. And if I go down just slightly on the frequency, down to 100 kilohertz, then it is the 10 volt as they promise. So I mean, this unit really works. Let's see how this, the square wave at 100 kilohertz actually looks really good. This is exactly how I like them to be, just a little bit smooth like that at the maximum output frequency. So of course, if I go down in frequency, so this is 1 kilohertz, then it is super nice and sharp. Wow, that is a fantastic generator. We gotta see what is inside. And the current consumption is 16 watts. Is there any? No, there's no visible difference. No matter what I poke around with here, it's just the same. Before we go and play inside, of course we need to try the lowest frequency. So I just tried to set the dial here for 1 hertz. I mean, we got 2 decimals on the hertz. Yeah. Look at that. I think this is also very close to 1 hertz. Oh man, it really works. Let's just flip it like that. Look here at the bottom, and this is something I really love about Bang & Olufsen. Look at the service lid here. All you have to do is like take those 2 screws out and remove this, and then you can access the entire PCB, the entire area of the PCB, and perform service without spending hours poking the entire unit to pieces. Wow, a lot of people could learn a lot from this service friendliness. See what I'm saying? This is the entire PCB, and we can access, I mean, almost all parts of it. If you're really good, you could probably access the switches down there. I see a little bit of a modification done here with a little wire, and goes to that switch, and then it goes to something else. A little resistor there, and a little funny diode doing some good stuff there. And there's no need to be afraid that the bottom plate's gonna go in and touch stuff, because see, there's a little flange down here, and there's also this little, so it's gonna be quite all right. So let's take off the top and have a look. It is no big surprise. It is very beautiful design, and everything is just in perfect order. I really like the way that they did all this. So the output attenuator is in a nice shielded box like this, and that means it is connected directly to the output. So the output amplifier and all that stuff is actually running at full swing or full power at all times, and then the output attenuator is just selectable output to the output B and C. So that is more or less how it is done. Then here from the output, all this you see here to the right, that is the meter. So it will be able to measure and indicate here the output. So that is all that stuff stuff you see right here. And all the diodes and transistors and the op amp here driving the meter. We've got two different output stages. The one here with the larger heat sinks. You can see here transistor 16 and transistor 17. That's the analog output stage made for a sine wave. And then the top output stage here, if you look at the two output transistors 33 and 32, as you see here, this is the square wave output amplifier. And all this stuff down here is of course all the different frequencies, all the different capacitors and all the good stuff around that. And that frequency counter unit is a standalone frequency counter unit. It's not, connected to anything except for the different frequency ranges. That's just moving the dots and stuff like that on the meter. It's not doing anything else. It's just measuring the frequencies, and that is why we don't see that many wires coming into that frequency counter module. We can of course look a little bit on the schematic just to show you guys that this is indeed a standalone frequency counter module. I really want to open this box so we can have a look inside. Hang on. That was difficult just to get that lid off. So that means we can't really get into that frequency counter module. I believe the reason why it is in a completely shielded closed box is of course they don't want all this digital nasty noisy stuff to infect anything of this nice analog clean area we got in here. And also there's a wall that is screwed at the top and the bottom here, and this is where you got the transformer and the power supplies. Everything here is of course regulated with all the different voltages and all that kind of good stuff. So that is nice and clean and good. Mains switch is only breaking one of the wires, but that's kind of how it was done in the good old days. I actually see a really good option for an upgrade, because look at this area we got right here. We could easily fit a more modern IEC connector right here, right? So that means you don't have this wire and annoying thing. And the ground is done absolutely nice and correct. So this is still legal today. Frequency, ooh, look at that, super high quality, but it's also really smooth and it's doing everything right. Oh, look at that. So this is there's a gearing here. So when I move this, look at that. It is inside this. There's some sort of it's probably made with ball bearings. This gearing. You probably feel it when you go all the way down, yes, and then it just goes around like that. So that is a classic ball bearing gearing. Yeah, look at the metal here and the shielding. Also from the front, again, it's doubled walled, kind of shielded, right? Yeah, this is how you do it if you want to do 100 dB or 106 minimum is what they tell you they can do. I took out the frequency counter module just to show you how it's done. All you have to do is press down on this black connector and then it will let you unplug the flat cable. And see, it is a double switch. You could have put those two contacts in parallel at least just to make sure you'll get a good contact. That could be one way, but you could also just disconnect both of the wires. I mean, yeah, and that is all the power supplies and regulators and whatnot. And if you've been playing a little bit with electronics for a few years, like I have done, you'll probably recognize this series of electrolytic capacitors as being known to be causing problems after like 20, 30, 40 years. And we are at that age now for this unit. So one should definitely change this type of capacitors just for the fun of it. I think we are very, very lucky that everything works super, super good at the moment, but they are known to be causing you guys problems. I also see a few of them here, super easy to access right here. But down here they're not so easy. You need to unscrew the frequency counter module to access them. Well, let's look a little bit at the frequency counter module. I mean, look at the front here. The plastic is milled. Oh. And then we got this. This is a counter with LED 7-segment driver and multiplex. And then the rest is just classic frequency counterparts. Ooh, crystal and everything nice. And of course this is why it is so accurate. Everything about this unit is just nice. I really love it. At a 4017, huh? Well, that is funny. And analog switches and a few diodes, and of course we got all those different switch inputs, and this is to select the different frequency ranges, and obviously this will affect how is the timing and behavior of this unit. I like this extra wire around the flat cables here, so this is kind of holding it and preventing it from damage when you open and close it. But if you look at the marks here, ooh, something down here is digging its way into the cable. So I hope this is not something metal. That's probably those two transistors. So that's just plastic. But after some years, you'll see problems. And where is this cable digging its way into what? I mean, look at that. I think I can see metal here, right? Yes, I can definitely feel the metal. Oh no. What is that? Oy. That is touching this metal as well. Oh my god, how can this work? You can see the metal through here. How the heck is that a good idea? So that hole should have been a little bit bigger. I mean, you can even see it has like marks of the wires. Let me try and... Oh, yeah. It is sharp as a knife. No way, this is not good. Yeah, that I will have to fix. So this is how I fixed it. Just added a little bit of painter's tape, actually 2 layers, just to be sure it's not gonna go and bite its way down here. I think it's also the side when you put, ooh, look at that. Oy. So this connector here is not really the most reliable. Oh, yeah, I kind of knew that. See? This is something I also need to play a little bit with. Classic problem with these push-in connectors here. So what you have to do here is actually take a screwdriver carefully and bend this socket a little bit up, so it will have a connection that is really weird. And at the same time, be careful, right here is mains. And another thing that I found, look at that screw. I mean, what if you put in a screw that is a little bit too long? Are you going to hit that? Yeah. This is of course before 3D assembly simulations and stuff like that, so oopsie doopsie. I would probably cut away those 2 pins so they are as short as possible, and they kind of did that with the others. But why didn't they cut those 2? That's the important ones. There's actually probably a bad soldering as well with one of these. Is it the same down here? No, there's no problems with the other screws. I've actually seen stuff like that quite a lot of times with screws on chassis, screws on something that goes in and touches stuff, or just nearly touches stuff, because they just didn't have a clue when they were designing this. Or it's also like 5 different people doing this design, right? Oh, what have we got here? There is a little acid damage, but it is, see, from this side you don't see it, but here there is a, it's probably just a manufacturing. Yeah, I think that was what I wanted to show you guys. Look at that. Oh, man. Come on, man. Oh, you got to see this. Have a look at IC14. So this is an optocoupler, and then this optocoupler is driving a transistor, and that is then the sync output. The ground of the sync output is connected to this sync or common switch, so that sync output can be completely isolated. But have a look at the supply voltage for that TR8, and the ground for all that is the same ground as the frequency counter, and that 5 volt for the frequency counter is also running off those windings on that on the transformer. So it's a completely isolated supply for counter and for sync output, and it's optocoupler isolated from everything else. This is just a nice recipe of super good clean signals to anything else. They really went all the way, those guys.